Hey everyone, welcome back to Formfully channel. In today's video, we are going to talk about RDD in PySpark, which stands for Resilient Distributed Dataset. RDD is one of the core concepts in PySpark, allows us to work with large datasets across multiple machines in a distributed environment. We are going to see a brief definition of RDD, features of RDD, how to create it, and what are the operations of RDD. So let's start. R in RDD stands for resilient. Resilient means that the system is fault tolerant. In the case of RDD, it means that even if part of your data or processing fails, such as a node going down in a cluster, Spark can recover and recompute the lost data. RDDs achieve this through lineage information, which tracks how the dataset was created and the transformation applied to it, allowing Spark to recreate it if needed. Example, if one of the machine processing your data crashes, Spark can automatically rebuild the lost part without any manual intervention. D stands for distributed. Distributed means that the dataset is spread across multiple machines or nodes in a cluster. This allows large dataset to be processed in parallel, significantly speeding up computation times. Each partition of the data is processed independently on different nodes, enabling Spark to handle large scale data processing across many machines simultaneously. Example, imagine dividing a large file into smaller pieces and distributing those pieces to different people so they can all work on it at the same time. Second D stands for dataset. This dataset refers to the collection of data. In the context of RDD, this dataset is a collection of objects, records, or rows that Spark processes. Each RDD contains a set of data that can be transformed or manipulated using various operations in PySpark. Example, the dataset could be a line of text file, rows from a database, or any collection of data that Spark will process in parallel. So, combining these three functionalities, an RDD is formed, which is collection of objects that are distributed across a cluster. This distributed structure allows us to process large-scale dataset efficiently in parallel. Now let's talk about some important features of RDD. By example scenario, we will understand the features of RDD. Example, you have a large log file that tracks server activity and you want to find all the lines that contains the word error and count how many such lines exist. This log file is too large to process on a single machine, so we use PySpark with RDDs to handle it. So first feature of RDD is immutability. Once an RDD is created, it cannot be changed. You can only create new RDDs from existing one. In the given example, we load the log file into an RDD, that is RDD word. Once this RDD is created, it stays the same. If you apply a transformation like filtering for error lines, a new RDD will be created, that is error underscore RDD, and leaving the original unchanged. So the original RDD is not modified here, but the new error underscore RDD is created with the filtered data. So once an RDD is created, it cannot be changed. Second feature is partitioning. RDD is divided into partitions and each partition is processed in parallel across different machines. It's like cutting a pizza into slices and everyone gets to eat a slice at the same time. Example, your log file is split into partitions and each partition is processed by a separate node in the cluster. Imagine your log file is divided into 5 chunks and each chunk is processed on a different machine, reducing the overall processing time. This allows large scale parallel processing, speeding up the computation. Third feature is fault tolerance. RDDs are resilient, meaning if one machine fails, Spark can automatically recover the lost data using something called lineage information stored for RDDs. It's like retracing your steps when you lose something. Spark knows how to reconstruct the data. Example, while processing one of the node fails, since Spark keeps track how the RDDs was created, it can recompute the lost partition from the original data, ensuring a task complete successfully. Even if node fails, Spark will automatically retrieve and compute the lost data without affecting the final result. Fourth feature is lazy evaluation. Transformation in RDDs are lazily evaluated, meaning Spark doesn't perform any operations until an action is triggered. RDD transformations like filter are not executed immediately. Instead, Spark builds a plan, a lineage of transformations, and only when an action like count is called, Spark triggers the execution. Example, in the given example, RDD is created from the log file and error underscore RDD, the new RDD is created using the filter transformation, but the data isn't actually processed until we call an action like count. Only when count function is called does Spark starts processing the data, applies the filter operation on all partitions. So this all are the features of RDDs. Next topic is how to create RDD. In PySpark, you can create RDD in two primary ways, that is parallelizing a collection in memory data or loading data from external storage, that is files, HDFS, etc. Let's go through both methods with example. First one is parallelizing a collection. You can create an RDD by parallelizing an existing collection, example list or array in Python. This is useful for small data sets or testing. In other hand, creating RDD from external storage. RDDs are commonly created by loading data from external storage system such as HDFS, S3 or local file systems. For example, you can load a text file or a directory of files. Let's understand example in both ways. In parallelizing a collection, we have created a list in Python that is data 1, 2, 3, 4, 5. Then created a RDD. The parallelized data converts the Python list into an RDD distributed across the Spark cluster. Then we have used collect function. Collect function is an action that brings the entire RDD data back to the driver program. In other hand, here we are loading data from a text file into an RDD. This line puts the file into an RDD where each line in the file is an element of the RDD. Then used take rdd.take file. Take file retrieves the first 5 elements from the RDD. This method can also be used to read from other storage systems like HDFS, S3 or local disk. You can specify the path to the file or directory containing the data. So key points in both ways. Parallelizing a collection is quick and useful for small data sets or when testing. And loading data from external storage is ideal for working with large datasets stored in systems like HDFS, S3 or local file system. Combining both, you can load an RDD from files and then apply a transformation. Let's say you want to load a text file and filter out lines combining the word error. This way, we can create an RDD from local Python collections and use when and text file is used when loading data from external storage. Next topic is RDD operations. RDD supports two main type of operation, transformation and actions. Transformations, these are operations that creates an RDD from an existing one. Transformations are lazily evaluated, meaning they are not executed until an action is triggered. Action, these operation is triggers the execution of transformations and returns result to the driver program or write them to external storage. Let's understand both types with example. Some common transformations include map, then flat map. So first one is map. In PySpark, map function is a transformation that applies a given function to each element of an RDD, producing a new RDD where each element is the result of the function applied to the corresponding elements in a given in the original RDD. Usage commonly used for data processing, such as converting formats, modifying values, or extracting specific information from each element. Syntax is uh, syntax is like new RDD and equals to rdd.map lambda x function x. Lambda x represents each element in the RDD. Function x defines what operation to apply to each element. Let's understand the example. Example 1, squaring numbers. Suppose you have an RDD of numbers and you want to square each numbers. So we have created the RDD with numbers 1, 2, 3, 4, and then used rdd.map lambda x into x to square the numbers. The squared underscore RDD, the new RDD is created, and we have used collect function, that is action, which triggers the transformation, and we will get the output 1, 4, 9, 16. Second example is converting to uppercase. You can use a map function to convert each string in an RDD to uppercase. We have two strings, hello and world. We used x.upper function to convert the given RDD strings into an uppercase. So we get the output hello world in uppercase. So map should be used to apply a transformation on each element independently, ideal for operations that transform or extract data from each element without altering the overall RDD structure. Second is filter function. Filter function is a transformation that creates a new RDD by selecting only the elements from the original RDD that satisfy a specific condition. It's commonly used to remove unwanted data or focus on specific elements within an RDD. Usage is useful for refining datasets, removing noise, or focusing on relevant subsets of data. Syntax is like rdd.filter lambda x condition x. So lambda x represents each element in the RDD, and condition x defines the condition each element must satisfy to be included in the new RDD. Let's understand the example. Example 1, filtering even numbers. Suppose you have an RDD or RDD of numbers and want to keep only the even ones. We have RDD of 1, 2, 3, 4, 5, 6, and we used filter function where we have x divided by 2 equals to 0 to filter out the even numbers. So the lambda function checks if each number is divided by 2, only the even numbers remains in the new RDD, that is even underscore RDD. Second example, filtering based on tuple values. If each element in the RDD is tuple, filter function can select tuples based on specific fields. In the given example, we are selecting the data which is greater than 30. So we will get Charlie 35, as only Charlie has value greater than 30. So when you want to refine your data by excluding elements that don't meet certain conditions, we can use filters. Filters useful for tasks like cleaning data, removing noises, or narrowing down to relevant data points. Third transformation is flat map. Flat map is a transformation that, like map, applies a function to each element in an RDD. However, unlike map, each input elements can be mapped to multiple output elements. This transformation is particularly useful for operations that involves splitting or expanding data. This is useful, commonly used for splitting strings, expanding list, or any process where one item can yield multiple results. The syntax is simple: rdd.flatmap and lambda x transformation x. Lambda x represent each element in an RDD, and transformation returns a list or a collection of items to be added to the new RDD. Example 1, splitting lines into words. Suppose you have an RDD of sentence and you want each word in the sentence to be a separate element in the RDD. Here we have RDD of hello world and welcome to PySpark. Here then we have used line.split using flatmap function. Here each line is split into words, and the flatmap transformation returns a flat list of all words in the RDD rather than an RDD of list. Second is expanding list. If each element in an RDD is a list, flatmap can expand each list's items into separate elements. In the given example, each list within an RDD is flattened into single sequence of numbers in the new RDD using flatmap. So when to use flatmap function? When you need to expand elements into multiple results, splitting sentence into words, like etc. And also useful for flattering nested structures or generating multiple output from a single input. Next transformation is distinct. Distinct is a transformation that returns a new RDD containing only the unique elements of the original RDD, removing any duplicates. Syntax is simple: rdd.distinct function. Example, distinct numbers. Suppose you have an RDD with duplicate numbers and you want to get only unique values. So here the distinct function removes the duplicates values and return the new RDD containing each number only once. Second, distinct words in sequence. If you have an RDD with string hello world, hello, hello world, distinct function can help retrieve unique sentences. In this case, distinct function removes duplicate sentence, keeping only unique ones, that is hello world, hello. reduceByKey. It combines values with the same key using a specified function and returns a new RDD with the combined value. reduceByKey is a transformation used specifically on paired RDDs, like RDDs with key pair values. It applies a given associative and commutative functions to reduce values by key, merging values with the same key into a single value. This operation is often used for aggregations such as summing or counting values associated with each key. Key-based reduction. reduceByKey works only on paired RDD, performing the specified operation on values with the same key. This is efficient aggregation. It reduces data across partitions before sending it to the driver, optimizing the network traffic. It is associative and commutative function. The function used should be associative and commutative, such as addition, multiplication, or finding max min. Syntax of reduceByKey is rdd.reduceBy lambda x by then x plus y. The lambda x, like this line, lambda xy, x plus y, the function is applied to each pair of values with the same key. Example of reduce by key, like summing values by key. In the given example, we have used reduce by key function to add values for each fruit type. Here, apple 1 and apple 2 are combined to give apple 3. Same way, banana 1 and banana 3 are combined to give banana 4. So, when to use reduce by key? When you need to aggregate values based on keys, such as summing, counting, or finding the maximum and minimum. For efficient key-based aggregation, especially useful in large dataset, we can use reduce by key. Now let's understand some of RDD operation, that is actions. First one is collect. Collect return all the elements of the RDD to the driver program. This is an action that retrieves all elements of the RDD to the driver node as a list. This is often used to weave or use the entire datasets in local memory, but it should be used carefully with large datasets due to memory limitations. It retrieves entire datasets, like collect function brings all data from the distributed RDD, returns a list. The entire RDD is returned as a list, allowing local operations or inspections. Use with collect function can cause memory overflow if used with very large dataset, as it gathers everything into driver memory. Simple. The syntax is simple. RDD.collect. Example, collecting small RDDs. Suppose you have a small RDD and want to see all elements locally. We have RDD 1, 2, 3, 4, 5 and use collect function to just see the RDD elements. Next, count is an action that returns the number of elements in an RDD. It often used to get a quick count of the records in our dataset without bringing the data to the driver, as count function only retrieves the count, not the data itself. So since count function doesn't bring data to the driver, it's more efficient than collect when only count is needed. Commonly used for metrics, like useful for calculating basic metrics or checking dataset size after transformation. Example, count the number of elements. We have RDD of 1, 2, 3, 4 as elements and used count action, so it will give 4. Next one is first action. It returns the first element of the RDD. Example, get the first element. We use RDD.first. So in the given RDD list, 10 is the first element, so it will output as 10. Then next one is take. Take action returns the first n elements of the RDD. In the given example, 5, 6, 7, 8 are the 4 elements and we use take 3. So first 3 elements printed as an output. Next is reduce. Reduce applies a function to the elements of the RDD to combine them into a single result. Basically, this function is applied commutatively to the elements of the RDD such that it reduces the RDD to a single result. Example, sum all elements in the RDD. We have elements 1, 2, 3, 4 in the RDD and we have used reduce function with x plus y. The x plus x and y are the 2 elements that are combined in each step. Operation applies to the x and y, and then reduce function start by applying the operation to the first 2 elements, then to the result to the next element, and so on until all elements are aggregated into a single result. So 1, 2, 3 and 4 will output as 10. Next one is save as text file. Save as a text file saves the RDD contents to a text file or directory if it's a distributed file system like HDFS. Example, save a RDD to a file. We have RDD of elements 1, 2, 3, 4, and we have used save as text file and given the path. So this operation will save elements into an text file. So in the conclusion, by all these examples of transformation and action, we understood that transformation are lazy. They create a new RDD but do not execute the actual computation until the action is called. And action triggers the execution of all transformations and return a result to the driver or write the output to external storage. Yeah, so we have come to an end. This is the summary. This concise overview covers the essential of RDD, its features, how to create RDDs, and the key operations to help explain RDDs in a simple and easy to understand format. So thanks for watching. Do like, share, and subscribe.